This is a video that introduces work and energy concepts and also takes you through some of the introduction lab data collection procedures. We'll start the conversation by just considering a phenomenon we've been looking at for several months and throughout semester one, in which we put a mass like this on a track and allow a fan to blow the object starting from rest, and we see motion like this. Now we might ask the question, what happened there? Many of you would reference what we have talked about and say we have an unbalanced force acting on an object. That unbalanced force causes an acceleration. You can kind of see the graph in the background there that was produced, and we'll look at that graph in a minute, but it suggests that that's indeed the case. So we look at a graph like this. Position versus time, velocity versus time graph. Did the object accelerate? It clearly did. Did the object accelerate at a constant acceleration? And many of you would look at this graph here and say, since it's linear, it's in the slope of the velocity versus time graph can be interpreted as the acceleration, that the acceleration is indeed constant. Some of you might go crazy and say, well, this is also parabolic, and I want to fit that with a parabola. And that's not usually how we would find the acceleration, but you could look at this A term and do that. Most of you would just take the slope of the velocity versus time graph and recognize that that is indeed the acceleration. If you're making sure these match, we would expect this A term to be half of that, and it does look like it is. So then you would consider kind of what's going on here. You've got a mass, and there's the force of the air, and that's a good thing to talk about, right? The air is actually the object that's pushing on the cart. So you would draw a free body diagram like this. You could consider the sum of forces in the y direction, and then and you would say, well, those are balanced in the y direction, and the only thing that's left in the x direction is unbalanced, and so causes an acceleration like this. And we'd write a sum of forces statement, and it would be this algebraic expression right here we could use to calculate that force. If we had any two of the variables, you can calculate the other. In this case, you would recognize that we could calculate the force that caused that acceleration if we knew the mass, and then use the acceleration from the graph. So here's the acceleration from the graph. Just switching this around, we know we can calculate that force. There's the acceleration right there. The mass of these carts is about 600 grams, and I've put it in as 0.598. So that can easily calculate the newtons. You're looking at this saying that would be kilograms times meter per second squared, and that is indeed a newton. And so what we did here was just completely consistent with first semester, and where we would say we might have introduced this initially as this course is really, and first semester is really about how forces change motion. We tighten that a little bit, and you might say unbalanced forces cause acceleration, and we even know how to relate those two. In this unit, we are introducing some new concepts, and we're saying instead of force changes motion, work changes energy. And the general outline for a equation that we're going to use, the general format, will look something like this, where we can see that there's some initial energy. Work is a process that changes energy. We can add energy, that shows a positive sign, but we can also take away so that the final energy is less than the initial energy. But this is the general outline of work changing energy. So you may have read this in the introductory reading last night, but the simplest way to define work, and this is mechanical work, this is how physics describes work, is force times displacement. Work equals force times displacement is another way to say that. You're looking at this, I'm sure you're interested in the units, and force in newtons times displacement in meters gives a newton meter. That's actually a joule. So that is, we have a term for that, and then the newton meter is the joule. And that brings us to the lab. The lab files, you're not actually going to collect the data. We've done this before. We don't have a fan card for everyone, so we just kind of made graphs with it, and you will that's kind of how you're going to analyze the data. The videos themselves are not that important, but they're embedded in there. So to get these, just a little procedure, you're going to go to the home page, go to the work and energy. This should be assigned to you, but you should be able to go down to lab activities and the work and energy introduction lab. It'll have a couple parts. You should be able to go in through the first one, but you could also get it to this link here. And as you scroll down, this kind of shows us a setup of it and how we consider this. Right here is the Logger Pro data files, and when you click on that, it's a relatively large file. It's a zip file, which is a compressed file, and it's going to download the whole thing. In this case, it appears to be taking a little time. There it goes. And then if I go to my downloads file here, there's the zip file. I can see it's the zip file because it's got a little zip. I want to right click on this and then say extract all. It'll say, where do you want to do that? I'm just going to keep it in the exact same place and then extract it. That'll take a second. And now I have the unzipped version of this. It took me right into it. So if I go back, like there's the zipped, there's the unzipped. Sorry. Yeah, I said that right. And then go into there, and then you're going to want this work and kinetic energy folder. If you want to organize this by type, you'll have all the CMBL files, which are the logger profiles here. If you ever want to see the videos, they're right in here, but they kind of reference each other. So let's go to this first video. And what we're asking is, yours should load quicker than this, but we're asking the question, how does the work affect the final state of the system or the final energy of the system? And to get the final energy of the system, we're going to measure the velocity at the end, and we want to show you how to do that. There's two research questions here. Both of them deal with work. So if you're looking at the lab, you'll see two different research questions. I'm going to address the first one, and then if I do the second one, it might be in a separate video. But this is the video you just saw. I can play this. It goes along. You see that, and then and that's really all I'm going to use that for. But these are the graphs that come with it. Now this one's very traditional for us. This one is different. It has been very rare for us to plot anything versus position. That is not unusual when you start considering work and energy. So a velocity versus position graph is something we're going to look at in a little bit. So this is effectively the graph we'll be getting. And so what I'm going to do here is quickly show the actual work and energy intro lab equation sheet, and then how we're going to kind of match this up. So what I have here side by side is the data that's produced by that motion and the data table that we're going to populate. A really key point for experiment one, research question one, each one of these rows requires a separate video. That's why there's like 6 different videos or something like that. So let's just start with this first one. And what the videos are labeled, this one says 0 degrees. This one just means that the fan is parallel to the displacement. So as the fan turns, the acceleration kind of goes down. So what this says here is that we want to use a constant displacement. So for every one of these, we're going to look at the same displacement. We're going to use the same displacement and change work by applying a different net force. Remember, we can change work by changing force or changing displacement. In this first one, all these are going to be constant, and this is going to be changing. In the second one, we'll change work the other way by holding this constant and changing this. But first things first. So all the data from here is going to go in this first column. First row. So how do we do this? Well, let's pick an initial and a final. Maybe we'll just say, let's analyze the first 0.5 and the first 0.5 meters of displacement. Once we decide that, that's going to be the displacement in all of these. So let's just take it to 0.5 here. Now at 0.5, it looks like the velocity, and I don't have to get this exactly right, but it looks like the velocity is about 0.6 or 0.7. So 0.6 or 0.7 would be about here. And so I'm just going to take the slope of that line right there. So I have the slope, and that's going to give me the acceleration that's going in there. I'm going to calculate the net force, and I'll show how to do that in a minute. And then we're going to calculate the work, and I'll show you how to do that. Now what we will need right here is the final velocity. So the final velocity, what we mean is what's the final velocity once this displacement has occurred. So it's very tough for me to see from this graph what the speed is when it's displaced 5 meters. That's the importance of this graph. I can see that once the object has displaced half a meter, that is the speed right there. Looks like about, you know, I'm right on top of that point. It's about 0.63. Now there's a couple ways you can do that. One of the ways you can do this with this examine function. The problem with the examine function is you'll notice it doesn't hit it right on. So this one's a little short of 0.5. Look at the position there. This one's a little over 0.5, but it tends to be a good way to get pretty close, and you're going to get good data sort of regardless. The other way to do this is to forget examine and just make sure you're on the graph like this, and then look at the little box down here. The problem is this just shows wherever my cursor is, and so, or my pointer is, and so if I move it down here, it moves. But as long as you're taking this point right there, that's a good one. So I'm gonna kind of freeze these, pull them in, and then show you how to process that. So here's the data pulled into one screen, just a graph that I just made. And how do we populate the data table? So keep in mind, a single video is one row here. Everybody can use the mass of 0.598. I'm also thinking everybody's going to use half a meter. You could use a different displacement, but you would have to keep a displacement constant. So if you chose a different, like 0.7 or something, you'd have to use that for all yours. We're considering the interval, or the displacement, in which the initial position was 0 and the final position was 5. Final minus initial, you can see, is half a meter. The acceleration is going to be obtained from the slope of the velocity versus time graph. We're then going to use that acceleration the same way we did in the introduction here. Multiply the mass times the acceleration, the mass from up here, the acceleration observed from the graph, to get the net force, and that net force will populate that cell. Now we have to calculate the work. This is our new equation. Work is force times displacement. We have the force right here. We have the displacement right here. When we multiply them by each other, we get this in Newton meters, which we also know is a joule, but we'll just list it as Newton meters. And then that populates that data table. Cell. The final velocity is the one that comes off of this graph. So remember when we had the crosshairs sitting over this point right here, we were looking at the 0.5. This right here came from when I was right at that spot, and this shows me that the displacement's 0.496, which is basically 5, and then the velocity was 0.6. If you don't believe it, just confirm over there. That seems about right. And so that is going to be the final velocity there. Now, that's one row. The next thing to do is to fill out the rest of them. If you're choosing the same displacement, which you should, these should all be the same. But this is going to vary because you're going to add the new graph, and the acceleration with the fan turned is probably going to be a little lower. That means the net force is going to be a little lower. That means over the same displacement, you should have a lower number here. And the final velocity you will achieve from that graph. So you need to, in order, enter them all in and then populate this. That's the task for day one. After we check that everybody has filled that appropriately, then we're going to graph this on the y-axis. And if you want to go ahead and do that, you can. But we're just really looking for the data table. This is going to be on the y-axis, the dependent variable, and this will be on the x-axis, or the independent variable. And we can argue about whether that's the right way to do it, but that's the way we're going to present the data, and it's much easier to interpret. So this is the x, this is the y, and that's going to be next, but right now just fill out the data table.